that data scientists do as part of training a model. Let's take an example. Imagine data scientist team is working on wine prediction model. Basically, a model that can predict quality of the wine. And they want to achieve at least 85% efficiency. This is the goal that they have. So they will start with the first experiment. So in the first experiment, they choose, let's say, random forest as algorithm, and they choose a CSV file as the data set. So they gather data from various sources and they got a CSV file. They trained the algorithm on the data set. They choose specific parameters. They did it on, let's say, a Windows machine. After the training process, they have the model. The model is saved, and the efficiency of the model, when they tested the model with testing data, they realized efficiency is 67%. Of course, they are not happy because this is nowhere near to their goal. So they will go with second round of experiment. Now, in this experiment, let's say they choose different algorithm. Let's call it as logistic regression. And they choose the same CSV file because they are confident about the data set. And they again started training the algorithm. They have the model file. This time the efficiency is 79%. They're a little happy, but still it is nowhere near to the required efficiency or their goal. So this time they choose a powerful algorithm like XGBoost, and they also worked on the CSV file by reducing the noise, eliminate the duplicates, and they choose a different environment as well. This time they choose Linux with high CPU and high memory, and the efficiency is 87%. So they're actually very happy, but they thought, let's continue our training process. Let's continue the experiments. Maybe we might get up to 92% as well, or 95%. So they kept on doing the experiments. The fourth experiment, fifth experiment, they did, let's say, 25 experiments. On the 25th experiment, they got 81%. So definitely they are not happy. They want to go with something near to 85 or more than 85, which they achieved in the third experiment. But let's say they did not track the experiments. That is, they did not keep a track of what algorithm did they use in experiment 3, what exactly is the data set, because data set must be modified in the successive experiments. So if they don't have the track of algorithm that they used, if they don't have the track of data set that they have used, and even if they don't remember on which environment did they do this experiment, what is the resources of this environment, then there is absolutely no point. They have to stick to the 81%, even though they had 87% efficiency at one point. So that's why experiment tracking is very, very important in machine learning lifecycle. But what do they actually track, right? Okay, experiment tracking is important. We understood at high level that they track few parameters as part of the experiment. But what are the real-time parameters? So data scientists usually track things like, of course, with the help of MLOps engineers, we will learn the tools in the successive lectures. They track information like parameters that they have used. What do you mean by parameters? So I'm talking about hyperparameters, something like learning rate. Now, this is what data scientists use within their scripts. So they decide on the learning rate. Apart from that, they use things like what exactly is the code version. So this is another important thing that is tracked as part of the experiment, because within the Git, there are multiple versions. Which version of the code is used? That is also important. Or which version of the algorithm is used. In every version, they might change the algorithm, right? So that's why code version, at least the commit ID or something, maintaining it is very important. Even dataset version. As I told you, in every experiment, they might change the dataset. They might add new entries to the dataset. They might remove entries from the dataset. So even they have to track the data set. Maybe integrate DVC here, something like that. And even metrics are important to track. Now it is not only about efficiency of the model, every metric has to be tracked. In the experiment tracking, they also have to track the artifacts. Because in experiment 3, they use XGBoost, they use CSV, they got 87% efficiency. They should also track the model file. Because in this experiment, they must have got the model file. If they save the model file, it will be very useful for them. So even tracking of the artifacts is important. Finally, system information. Now, a lot of time people ignore the system information, but if they take the same XGBoost, if they take the same CSV file, let's say they perform training process on Windows with some specification, the efficiency might come down to 86%. But on Linux with specification, a specific one, they got 87%. Even this 1% efficiency is important. So that's why as part of experiment tracking, system information should also be tracked. So this is about experiment tracking. Once again, just to repeat, experiment tracking is a process of recording everything that data scientists do as part of their training process. Usually, they do multiple experiments because they don't reach the required efficiency in the very first experiment. So as part of experiment tracking, to know in which experiment they got the best efficiency, they have to keep a track of things like parameters, like what exactly is the learning rate, code version, which algorithm or which Python script they use for the training process, dataset, which version of the dataset helped them with best efficiency, metrics, the accuracy of the model. They also have to keep track of artifacts. On every experiment, they have to save the model files so that they can use a specific model file in the future. Even system information. So this is about experiment tracking. In the next lectures, let's learn more about experiment tracking and implementation. What is MLflow? So in the previous lecture, we learned about experiment tracking and why experiment tracking is very important for data scientists. Now, MLflow is the most widely used platform for experiment tracking. Of course, MLflow is also used for other purposes like versioning the models and deploying the models. But the most popular use case of MLflow is experiment tracking. Now you might have a question, but Abhishek, what is the purpose of a tool for experiment tracking? Data scientists can simply use an Excel sheet. To be honest, this is a very good question because a lot of data scientist team today still use Excel sheets or some kind of notebooks to record their experiments. For example, they create an Excel sheet. Let's say one team is working on wine prediction model. They start with an Excel sheet where they note down, okay, experiment 1, these are all the parameters. Something like which hyperparameters did they use, what virtual environment did they use, algorithm, dataset, and then experiment 2, again, they keep note of all the parameters. This way, let's say they conducted 100 experiments. They keep track of all the 100 experiments in the same Excel sheet. Now, this is a very bad approach, and this is anti-MLOps pattern because one, we are all humans, even data scientists are human, and sometimes they might forget a particular experiment. Let's say they forgot to record 67th experiment out of 100 experiments. And unfortunately, that 67th experiment was the most efficient experiment. Now, all of this effort is wasted because they lost track of the most important experiment. So with manual effort, this is one of the problem. Second, there is no centralized approach in this way. That means team A working on wine prediction model, they have an Excel sheet. team B working on, let's say, weather prediction model, they have a different Excel sheet. Now, end of the day, organization will have multiple Excel sheets tracking experiments of different models, which is a complete decentralized approach and which is a complete mess. 1 year down the line, if they want to go and see performance of something, they have to first figure out in which Excel sheet they have that particular thing. On top of that, there is no standard practice as well. One Excel sheet might look completely different from other Excel sheet. Because of all of these reasons, tracking experiments in Excel sheets or notebooks is a complete anti-MLOps pattern. So in this case, what organizations have to do is they should go with experiment tracking platforms like MLflow or weights and biases. Now what MLflow does is that it completely automates this approach and it provides a user interface. All that management or data scientists have to do, they have to select, let's say, 2 experiments. They have to click on them and compare the 2 experiments. Within the user interface, MLflow shows what is the difference between the parameters of 2 experiments. Very, very efficient, right? Now you might ask, Abhishek, what is the scope of MLOps engineers with MLflow? So MLflow is a shared responsibility. So one, MLOps engineers. So MLOps engineers set up MLflow for the organization. It can be on the virtual machine. It can be on Fargate or serverless approach. It can be on Kubernetes or on containers. Anything depending upon organizational scale. But this is very important to have a centralized MLflow server for the organization so that all data scientists can use a single MLflow server. Now, data scientist responsibility with MLflow, they have to use MLflow model within their Python scripts and they have to record the information within their Python scripts. So by default, if you install MLflow, nothing happens. Data scientists should use the MLflow model. They have to connect to the created MLflow instance, the tracking instance, and they have to push the records to this MLflow instance. Don't worry, we will see this everything in the practical, but all I want to say here, there are 2 parts for organization to implement MLflow in the production ready approach. Number 1, MLOps engineers should install and set up MLflow. 2, data scientists should work on instrumentation. What instrumentation? So basically, they have to use the MLflow module in their Python scripts. They have to connect to the MLflow instance, and then they have to record the parameters that they are using for each experiment. So once they use the MLflow module in their Python scripts, this process becomes automatic. Every time they run the Python script, the instrumentation part will record the parameters and store them in the MLflow instance. Even if they run it 100 times, all the 100 ML experiment records will be stored within the MLflow instance. I hope this part is clear because in the next lecture, we will proceed with MLflow installation. One final time. MLflow is used for experiment tracking. This is a very powerful platform. Now, if an organization wants to implement MLflow in production, they have to do it in 2 levels. Level 1, MLOps engineer will set up MLflow for the organization. It can be on the virtual machine, Fargate, Kubernetes, anything. 2, data scientists use the MLflow Python module. They connect to the MLflow instance and they log the information to the connected MLflow instance so that all the experiment tracking is at one place. This is about basics of MLflow. In this lecture, I'll show you how to install MLflow on your local machine. This is not for production use case. This is just for your demo purpose or your proof of concept. But don't worry, in the future lectures, I'll also show you how to set up a production level MLflow instance. Let's get started. So I'll start with creating a directory for this lecture. So let me call this MLflow basic install. And within this directory, I will set up a Python virtual environment. You don't have to copy any commands. I'll share all the commands in the GitHub repository. So Python 3-m virtual environment dot venv. Let's also activate the virtual environment source dot venv bin activate. Okay, so we have virtual environment setup and also activated. Now to install MLflow, we just have to run a single command python 3-m pip install MLflow. That's all. So this will set up MLflow on the local machine. However, we are yet to configure the MLflow instance. This will only do the installation part. So this is downloading all the dependencies and finally it is installing MLflow. There you go. So now we have MLflow installed. To configure it, we will run this command MLflow UI ---- backend store URI SQLite MLflow.db -- port any random port. So a lot of people use 5000 as the default port. That's absolutely fine. But if you have something else running on 5000, you can choose any random port as well. Okay. So what is this command exactly doing? So this will set up MLflow UI on port 7006 and it will use SQLite DB on your local machine for tracking purpose. Why MLflow needs a DB? Because as we learned in the theory part, it stores record of all the experiments. So it needs a database. Okay. So let's run this command. This will take few seconds. I mean, this will take less than a minute, but once it is done on port 7006, you will have MLflow running. Okay. So it says started parent process and application startup is also complete. Let's go back to the browser and see. So on the browser, I have MLflow running on 7006. This is how it looks. So this is the home page. Here, there is an experiment tab. If you click on the experiment tab, once data scientists push their data or as they start pushing the record of their runs, you will see them here. We will learn that once we set up the production MLflow instance, right? Because once we have the production instance, I'll also show you through a Wine prediction model how they actually push the records and how they compare between two different records. For this lecture, you have learned how to install MLflow on your local machine. In the previous lecture, we learned how to install MLflow on the local machine. But these days, most of the companies use Kubernetes. So maybe to convince your management or to convince your data scientists to get started with MLflow, you might have to install and configure MLflow on your Kubernetes cluster. Again, in this lecture, I'll show you how to install and configure MLflow on your local Kubernetes cluster. This is just for your demo purpose or proof of concept. In the next lecture, I will show you how to set up a production level MLflow instance. Let's get started. So for this lecture, we need a local Kubernetes cluster that can be anything. So you can go with a kind cluster, you can go with Minikube cluster, or if you want, you can also go with EKS or AKS clusters. So I will use kind Kubernetes cluster because it is very, very light in weight. So all that I have to do is run this command kind create cluster hyphen name. Let me call this as basic MLflow cluster. I need to have Docker running for this. I already have Docker running on this machine. Okay. So in less than a minute, we should have a Kubernetes cluster ready. And on this cluster, I will show you how to install MLflow. There you go. So we have the kind cluster running. Now, how do we install MLflow? So there are two ways. One, either you need Kubernetes manifest for MLflow or you need a Helm chart. Now, there is no official Helm chart for MLflow, but if you go to community charts, so this is the community charts, community maintained Helm charts for open source projects. If you get to this, here you have community charts for popular open source projects like MLflow, N8N. We will go to the MLflow community charts and we will use them. Of course, you can also create Kubernetes manifest, but it will take extra time. When you already have something, you can use it. But don't follow the steps here. Some of these steps are wrong. I even created a pull request. So make sure you go to our GitHub repository and use the steps that I have shared. But the reason why I'm showing you this, we will be using the Helm chart that they have set up, right? So we'll be using this particular Helm chart. Okay. Now, assuming you also have Helm and kubectl installed on your local machine, let's start with running the command helm repo add community charts. Perfect. It says I already have the repo. So let me just update the repo. Helm repo update. If you don't have Helm or kubectl installed, it's very simple. Just head to their official installation pages and install kubectl as well as Helm. Perfect. Now we have the repository as well. So we will run the command to start the community Helm chart. So for that, I'll run this command helm install MLflow community charts MLflow. That's all. So run this command and within no time, you should have your MLflow instance running. So what does this say here? So it says your MLflow pod will be in the running state in few minutes. Once it is running, you can use kubectl port forward to access MLflow from this Kubernetes cluster. Let's see that. So if we run kubectl get pods, so it is still in the container creating status. Usually I've seen this taking 1.5 minutes, close to 1.5 minutes. So let's wait for 90 seconds and then let's see if this is in running state. Perfect. So after 81 seconds, this is in the running state. Now we can just use the kubectl port forward command. Kubectl port forward pod, name of the pod, right? So this is the name of the pod, followed by, we will use a port. So let's use the same port that we used in the previous lecture, 7006 colon 5000, which is the default port on which MLflow container is running. Hyphen address 0.0.0.0. So this extension is used, or this argument is used to basically bind the port to your local host. So when you are accessing it from the browser, it is recommended to add this particular thing. Great. So now we should have MLflow running on port 7006. Let's see on the browser. Right now I don't have anything running on 7006. I stopped the previous installation. If I refresh this page, I have MLflow instance running. Great. So again, you can head to the experiments tab. Right now, we don't have anything. In the next lecture, when I show you production level MLflow installation, I will also tell you how data scientists interact with that MLflow instance. So next lecture is going to be very, very interesting. Make sure you follow it and also implement it. In the previous lectures, we learned how to install and configure ML for demo or proof of concept purposes. In this lecture, let's learn how to set up MLflow in production environment. So in this lecture, I will install MLflow server in a Kubernetes cluster, just like last time, but instead of storing experiment records within the Kubernetes pod, I will connect the MLflow server to an external database, something like Postgres. And I will set up the Postgres database using AWS RDS. So this Postgres database is going to be managed by AWS. You might have a question here, but Abhishek, what we learned in the previous lecture is fairly simple. All that I have to do is to run a Helm command, and Helm installs and sets up MLflow on the Kubernetes cluster. This is definitely true, but if you observe carefully, what we set up in the previous lecture was stateless architecture. And this stateless architecture cannot be used in production. I'll give you a simple example. So in the previous lecture, we set up MLflow instance, and this MLflow instance was running in a Kubernetes pod. And all the experiments that are pushed will also be saved to the same Kubernetes pod, because in the previous lecture, we were using SQLite DB that is set up using the Python, or that is running within the same Kubernetes pod. Now, you know, in Kubernetes, pods are ephemeral in nature. That means a pod in Kubernetes can go down for n number of reasons. It can be crash loop back off, lack of resources. In any case, if the pod goes down, because we choose the stateless architecture, all the data that is within the pod is also lost. Of course, pod comes up. So you will have new MLflow instance running, but that new MLflow instance will not have the data. Now understand how problematic this is, because all the data scientists within the organization rely on the same MLflow instance. They have all their experimental related information stored to the MLflow instance. And because it is ephemeral in nature, because it is stateless in nature, if the pod goes down, all the information is lost. So it's a huge loss for the data scientists. That's why we should set up stateful architecture in production. Now, how this architecture becomes stateful? Imagine you have your MLflow server running within the Kubernetes cluster. So this is just the instance hosting the UI and the server. If this goes down, because the data, everything that data scientists pushed is stored within the database, and this database is managed by AWS. So there is no chance this database can go down, and even you can set up some backups. You can configure automatic backups. You can configure automatic snapshots, and even you can go back to a particular point of time, right? With all of these features, your RDS enabled Postgres instance is completely robust. So this architecture is stateful in nature. But Abhishek, I can also set up MLflow server in a Kubernetes pod and Postgres in a different Kubernetes pod. And I can make this Postgres database stateful using persistent volumes. Definitely, yes, you can also go with this approach, but there is additional maintenance with this approach. You have to constantly upgrade your Postgres database, and also you have to make sure the persistent volume claim, and everything else is created. So this is also a good approach, but this is recommended approach 1. This is recommended approach 2. And even the official community charts recommend this approach rather than this approach. Perfect. So now in this lecture, we will set up one more time. We will run the MLflow server within the Kubernetes cluster and connect the MLflow server to the Postgres DB running outside the Kubernetes cluster within AWS. If you're on Azure or GCP, you can use equivalent services on Azure or GCP. So before I show you these things in practical, let's write down the steps. So step 1, I will set up RDS instance. So I'll basically set up Postgres database on RDS. This is step 1. Step 2, I will connect to the Postgres database and set up MLflow DB within the Postgres database. Why? Because by default, the Postgres DB instance comes with the Postgres database. It is not a good approach to update the default database. So I'll set up a dedicated database for MLflow. Step 3, once the MLflow database is available, I will create MLflow user within the database and grant all the permissions to the MLflow DB. Step 4, I will install a Kubernetes cluster, and within the Kubernetes cluster, I will run MLflow server, and to this MLflow server, I will provide access to the MLflow DB using MLflow user, right? So using this MLflow user, the MLflow server in the Kubernetes cluster will connect to Postgres database and it will update the experiment records within MLflow DB. So these are the steps that we are going to perform. First of all, you need AWS account. So I already have my AWS account and I have already set up the Postgres database. Because this will take 10 to 15 minutes, I have already created this. Never mind, I'll show you the steps how to create them. First of all, search for RDS. You can follow the same steps. Click on RDS. Once you're here, click on databases. Click on create new database. Instead of full configuration, go with easy create. If you are a beginner, this will help you a lot. And choose Postgres as the database. Provide a unique identifier. That means provide a unique name for your DB instance. For example, something like, Abhishek, Udemy demo, followed by MLOps learning, something like that, which makes the name unique. Now, ideally, you should choose the DB instance size as production because you get 4 vCPU, 32 GB, 400 GB. But if you look at the pricing, this is almost $2 per hour and this is $0.019 per hour. So when you're learning how to set up MLflow in production, use the sandbox instance because you will not be dealing with huge amount of data. In your organization, make sure you go with this option. Now, either you're using this or this. Once you're done with the demonstration, please delete it so that you will not incur any additional charges. And finally, set up a password to connect to this DB instance once it is available. And copy the password that you have created because this will be used when you try to connect and make configuration changes. For example, as I told you, we will be creating a database within this instance. So you have to connect to the DB instance and you have to create the DB. So you have to keep this password safe. And finally, click on the create database button. That's it. In next 10 to 15 minutes, once you do this, in the next 10 to 15 minutes, you will have the database instance ready. Something like this. Okay, so assume your database is also ready, just like mine. What are the next steps? So click on this. You will find endpoint to connect to this database. Because we are done with this step. Next step, we have to create MLflow database within the instance. So to do that, I have to connect to the instance. Going back, this is the endpoint. I cannot do anything from the AWS console. So I need a client to connect to the DB instance. It's very simple. You can just go to PostgreSQL official page, click on the downloads button, and here you can install PostgreSQL client according to your requirement. If you're on macOS, you can just run brew install pql, something that I've done. But if you're on Linux, follow these steps. If you're on Windows, follow these steps. What I have done, I just ran brew install PQL. So now once you have the PQL, once you have the PSQL, just run this command PSQL -h followed by name of the host. So this endpoint -p, that is the port. The port is constant 5432 followed by username, which is Postgres. Now once you click on the enter, ideally it should connect, but this will fail or this will take a lot of time and eventually fail because I'm trying to connect from my local machine. Now, if you're trying to connect from EC2 instance, that is instead of your personal laptop, if you're using EC2 instance, it will work fine only if both your instance and this database are in the same VPC. Why? I'm sure many of you know this concept. In AWS, there is something called VPC, Virtual Private Cloud. Only two instances within the same VPC by default. You can enable VPC pairing, but only two instances within the same VPC. And if they have common subnet between them, they can talk to each other. Now, in our case, we have RDS instance within a VPC, and we have, I'm using my personal laptop that is outside the AWS network. So when I try to connect it, the request is blocked. In fact, I cannot connect to internal IP address of this RDS instance. So what I have to do here, I have to enable public access to the RDS instance. If you're doing it from EC2 instance or Lambda server, you don't have to make this change. So the change is very simple. Go back to the Postgres DB instance, click on the configuration section. Let me show you connectivity and security. Scroll up, you will find modify. Click on the modify. Again, scroll down to the section where you find the connectivity. Click on the additional configuration. Here you have an option, public access, not public access. Click on the publicly accessible. Scroll down, click on the continue button. Apply during the next scheduled maintenance window or apply immediately. Go with apply immediately. Modify DB instance, and this will take up to 5 minutes. And after 5 minutes, you are ready. Okay, there we go. It says successfully modified Postgres DB, the complete name of the DB. Now let's go back and click on the enter button. It should ask for password. Great. So when it asks for password, that means the connection is successfully established. Cool. So I'm connected to the default database, that is the Postgres database. You can just run -l to list all the databases. So these are the databases, Postgres, RDS admin, template. Right now we are connected to this one. But as I told you, it's not a good practice to use the default database. So we will set up MLflow database. This database can also be shared with other MLOps use cases. So again, that's another reason why having a dedicated database for a particular use case is good. Now to create the database, we will run this command, create database followed by name of the database. So I'll choose the name of the database as MLflow. You can actually find these commands within the official Helm chart repository, the documentation as well. But there is some issue with this documentation. I already created a pull request for it. I hope this pull request gets merged soon and the documentation is corrected. Meanwhile, I will share the steps in the GitHub repository as well. Okay, so first step, I created the database. Now I'll create a user. Create user. Let me call this user as MLflow_user with password. So I'll use a random password because anyways, I'm going to delete this database after this lecture. MLflow underscore password. Okay, I'll use this as the password. Great. So the user is also created. Now, the next thing that we will do is we will grant all the privileges to this user on the database. Grant all privileges on database MLflow to the user MLflow user. Now, this is the missing part in the documentation. So from the pull request, I'll copy the step. Grant all privileges on schema. Let me paste it here. Grant all privileges on schema public to MLflow user. Okay, so let's run this as well. Now we have set up the MLflow database. We have set up MLflow user also with the right access. Now we will just step out of the database. Great. What is the next step? Okay, we are done with this. We are done with this as well. Now let's head to the Kubernetes cluster and run the MLflow server. In my case, I will choose Minikube or Kind Kubernetes cluster because in the previous lectures, I choose Kind. I will continue with the same Kind Kubernetes cluster. So it's very simple. Just run Kind create cluster -- name is equals to name of the cluster. Let me just call this as production MLflow setup. Now, if you have credits, you can go with AWS EKS installation itself, and you can set up the complete thing on AWS. So you can have your database in AWS, even your Kubernetes cluster also on AWS. But if you're looking for a cost-effective approach, you can go with Kind cluster or Minikube cluster for your learning purpose. In your organization, you have no option. You should go with a production Kubernetes cluster itself. Okay, saying that, let me click on the enter button, and in less than 30 seconds, I should have my Kubernetes cluster ready. Great, it's almost ready. Starting the control plane. There you go. So now we have the Kubernetes cluster as well. Let's install MLflow server. So to install the MLflow server, this time, along with running the Helm chart, just like last time, we will run the Helm chart, but now we also have to update the database connection either using values.yaml or using -- set parameter. So what are we passing? This is same Helm install MLflow within the namespace MLflow. So here set backend.store database migration. This is for the database migrations. Postgres is the database. We have to update the Postgres host name. So what is the host name for the Postgres? Let's go back to the AWS, click on it, copy the endpoint. Cool. The port is the same. Database name is also same, MLflow. Database username is also same, MLflow user. Password in my case is MLflow password. But Abhishek, how can I secure this in the organization? If I'm using Helm chart, I want to keep this also sensitive. You can basically use the secret file and you can store this username and password in the secret file. Or you can also use AWS system store parameter store. I'll run this command, but this will fail because I haven't chosen the right namespace. Namespace MLflow is not created. So what I'll do is I'll just go with the MLflow namespace itself, but I will first create the MLflow namespace. So let me just copy this, Control C, kubectl create ns MLflow. Now let me rerun the command. Okay, what does it say? So it says expected 2 arguments. Okay, there is basic indentation issue. Let me just copy paste the command again. Okay, namespace is MLflow, username. Let me just paste the host name. This is the endpoint, paste it back, MLflow user and MLflow password. I think this time we should be good. MLflow password. There you go. So now It says in next couple of minutes, you will have your MLflow pod running. And once it is available, you can go with kubectl port forward. Now, because I'm running this on the kind Kubernetes cluster, the only difference is that I cannot expose the service using load balancer service type, or I cannot set up ingress resource because it is running on my local machine. That's the only difference, right? If you are going with EKS, you can enable ingress for this service. If you're doing this on local Kubernetes cluster, just like me, you can use kubectl port forward. Let's do kubectl get pods -w to see the status of the pods. Okay, oh, my bad. I have to check that in the MLflow namespace, MLflow -w. Perfect, there you go. So MLflow server is running, and because it says the status as connected, that means it is also connected to the DB instance. Why? Because in the production MLflow instance, unlike the usual one, there is a init container. For example, if I just do kubectl edit pod followed by name of the pod to just show you the configuration and MLflow. So you will notice here in the container section, there are actually two containers. One container is the init container, which you don't get in the local installation. The responsibility of the init container is to just verify if MLflow is connected to the Postgres database. Okay, so you can see here, there is an init container. The init container is just running a script. Okay, and it will verify if the connection is established successfully. If not, init container itself will get into crash loop backoff state. So that's why we can confirm the connection is also successful and MLflow server is also running. Anyways, let's implement kubectl port forward. So how do we do that? So we just need the name of the pod. Again, I'll just do kubectl MLflow. So kubectl port forward pod followed by the name of the pod. Let's paste it here. Great. And then I will have to just provide a port on the local host. So let's say I'll map this to 7004 this time. And the port on which MLflow is running, as I told you, the default port is 5000. Let's use the same. I also have to provide the namespace. Let me bind it to the address first, 0.0.0.0. And I will provide the namespace at the beginning of the command, kubectl -n MLflow. Okay, now let's try this. Forwarding. The tunnel is established between 7004 on my local host. So you can see the MLflow instance is ready. And this time, this is a production MLflow instance. Of course, even now, there are no experiments. But in the next lecture, I will show you how data scientists push their experiments to this MLflow instance. For now, this is how you install and configure MLflow instance at the production level. In the previous lectures, we learned how to install and configure MLflow. In this lecture, let's understand how a data scientist push their experiment related information onto the MLflow instance. But before that, let me quickly show you how to connect to this MLflow instance from the terminal. Right now, I'm connected through the browser. I can click on the experiments and I can also create an experiment. But usually this is done through automation, that is through Python scripts. I mean, data scientists create experiments, they track their experiment related information through the Python scripts. But before we understand that, I will show you how to access this instance through the terminal. First, I'll take my terminal. Let me create a directory. I'll call this as MLflow connect. Let me switch to the directory MLflow connect. All that we have to do is to install Python MLflow module. Before that, I'll create a Python virtual environment, python 3-m venv.venv. Let me source the virtual environment, source.venv bin activate. Okay. Now to install the Python module for MLflow, let's run this command, python 3-m pip install MLflow. Great. So it will download all the dependencies and it will also install MLflow module on this virtual environment. Once you deactivate the virtual environment or delete the virtual environment, you will not be able to access it because you deleted all the modules in the virtual environment. Okay. Now, how to connect to this MLflow instance? Very simple. You can use the Python command line as well, or you can write a short script. But because this is just 3 lines, let me do it from the command line. First command, import MLflow. So we will be able to do it because we are in the same virtual environment. Okay, it is being imported. Once that is done, we will set up the tracking URL for this MLflow instance. In my case, it is localhost 7006. So let's set the tracking URL, MLflow, the module that we just imported, dot set tracking URI, localhost 7006. Great. Now let's say MLflow dot set experiment, my first experiment. Let me just call it as my first experiment, MLflow. Okay. Now, as soon as I enter, what happens here, the MLflow module, it tries to create the experiment with name, my first experiment MLflow, on this particular URL. So that's what it says. Experiments with name does not exist. So I'll go ahead and create the experiment. Let's see. I'll refresh the experiments tab. And here I have my first experiment, MLflow demo. You can do the same thing in a small script as well. For example, you can write a small script, connect dot something like connect1.py. And here you can just say import MLflow. Then you can say MLflow dot set tracking underscore URI followed by the tracking URI. And you can say MLflow underscore set experiment followed by the name of the experiment. Instead of writing the script, I just use the Python command line. Okay. Now this is clear how to connect to the MLflow instance, how data scientists connect to the MLflow instance. It's exactly the same, but instead of writing a script, what they usually do, they update their existing script. So let's say there is a data scientist already working on wine prediction model. Okay. So a data scientist is already working on wine prediction model. So the data scientist must have already created a train.py file. Now, instead of writing a new file, what data scientist usually does, if you introduce MLflow into their ecosystem, data scientists will add maybe 5 to 6 lines or more lines to the training.py so that connection to the MLflow instance is established. And every time they run the train.py, the experiment related information is pushed to the MLflow. This is what exactly happens. Now you might have a question, but Abhishek, why should I learn this entire thing? Because it's data scientist responsibility. I'm done with creating MLflow instance. To be honest, that is true. But because MLOps is evolving, a lot of companies even today, especially startups and large scale organizations, the legacy companies, they have data scientists who are still running the experiments and recording the information on the Excel sheets. Now for them to onboard to MLflow is a very big step. So as MLOps engineer, sometimes you might have to perform a proof of concept and show them how exactly it works and what advantage would they get. Only then they will be convinced. That's the whole reason why I'm explaining you how data scientists actually use the MLflow instance and track their experiment related information. I hope it is clear. So now let's see using the wine prediction model that we used during the DVC section. So we use this GitHub repository during data versioning, understanding how data versioning takes place and how data scientists just push the .dvc file and store the data, especially the data set, onto the remote version control systems like S3 bucket. So let's imagine a data scientist already has this. They have pushed their train.py along with .dvc onto the GitHub repository. After a while, they are back and now they have to set up MLflow as well for this project. Let's see how data scientist does it from the scratch. So again, we'll go back to the terminal. I'll go back to the home directory and first, the data scientist would clone this repository. Okay, let's do it. Git clone wine prediction model. Okay, then the data scientist would get into this directory. Awesome. Obviously, every time data scientist creates a new directory or works on a new system, data scientist would set up the Python virtual environment as well. So Python 3 -m venv.venv. You must be seeing me doing this particular command a lot of times, but trust me, this is very important to avoid dependency conflicts and messing up with your system. Okay, then the data scientist would source the virtual environment, source.venv, bin activate. Perfect. Now, data scientist has cloned this repository, but if you look at the data folder, data set is not available. So obviously what data scientist would do, Python 3 -m pip install DVC. Okay, so now this will install DVC, but the data set might be on the local system or it can be on the remote system. In this case, because the data set is not on the local system, data scientist would look for this file .dvc config. From this file, data scientist understands, okay, so the data set is pushed to this remote S3 bucket. So I should also install Python 3 -m pip install dvc_s3. Okay, so now this will also install dvc for S3. Now the data scientist can simply do dvc pull. So this is the first step and very important step before using MLflow. Okay, now if data scientist does ls data along with the dvc file, actual sample file is also available. That's the actual data set is also available. Awesome. Now data scientist will update their existing train.py. So this is the existing train.py. So in the train.py, data scientist just loaded the CSV file from the path, used linear regression as the algorithm, and trained the linear regression with the data set, and then stored the model onto the local disk or a particular location on the local disk and log the metric related information onto a file. That's it. So this is the traditional train.py file. Now data scientist should update this train.py. Don't worry, I have things already updated. I will copy the new train.py and show you how exactly it looks like. On a high level, it would look the same what we did while connecting to the MLflow instance few minutes back. That is, we imported MLflow, we used mlflow dot set tracking URI and mlflow dot set experiment name. Data scientist would do similar thing in the train.py. So I'll remove this train.py and I will copy the one that I already have. CP, I have it on my local disk. Don't worry, I will share this within the GitHub repository, so you don't have to write it again or copy it somewhere. There you go, train.py onto this location. Let me show you how this looks like. Vim train.py, it almost looks the same. Now when you look at main, so this is where the program execution starts. The first command is different. Args is equal to parse args. So basically, instead of hard coding values, in this case, data scientists just use the arguments. For example, what is the test size? That is, what is the test data size? 20%, 30%. In this case, just for understanding purpose, I use the test data size as 0.9. Of course, this is a very bad practice. You cannot have test data size more than the training size. But just for logging the information, the test data size is chosen as an argument. Similarly, max depth as an argument, name of the experiment as an argument. Let's provide it with a different name. So I will choose the name of the experiment as Wine Demo or Wine Prediction. Let me call that probably a better name, Wine Prediction. So basically what these arguments are doing, instead of hard coding it, when I showed you the demo few minutes back, mlflow.set tracking URI, I hard coded the tracking URI here. I hard coded the experiment name here. Instead of that, we are parsing the arguments. Basically, we are taking the arguments and passing the arguments to the main function. That's it. If you want to make it look simple, you can also hard code these values. Next. Okay. So mlflow.set tracking URI, mlflow.set experiment, the same way, loading the CSV file, that is loading the data set. Okay. Again, very common thing. Reading the arguments. Okay. Here, choosing algorithm and training the algorithm. And finally, this is one additional step, that is again logging few important parameters to the MLflow instance. So the initial lines of the script here, only set tracking URI. This is to instruct MLflow. What exactly is the tracking URI? Where is MLflow hosted? And this is experiment name. But within the experiment, right now, if you go to my first experiment, there are no values. So there is no tracking information. So that's why in the Python script, not only setting experiment name is important, but the data scientist should also log parameters like what is the test size. Push the test size information to the MLflow. MLflow.log parameters random state. Push the random state information to the experiment that we just created. Perfect. And then training the model using random forest regression. And finally, predicting the model and also pushing the model prediction related information onto the MLflow instance. If you observe carefully, the commands are very simple. First, mlflow.set tracking URI, mlflow.set experiment. And whenever data scientist feels like I should log this information from the script, all that they have to do, mlflow.log parameter followed by name of the parameter and value of the parameter. That's it. Let's see what happens when data scientist runs this script. But before that, we should add to the requirements.txt a new one, that is mlflow, the dependency. Python 3 -m pip install -r requirements.txt. Okay, now the requirements are installed. Once this is done, let's go ahead and run Python 3 train.py. Right now you can see there are only two experiments, my first experiment and default. Once we run the script, you will see a new experiment called wine prediction. And within the experiment, you will also find the values that data scientist logged in the script. Python 3 train.py. If there are any issues, we'll also try to correct them. Let's not worry about the issues. Okay, Python 3 train.py, it is taking time, which is a good sign. Probably it is trying to push the information. First, it should say could not find wine prediction experiment. Okay, so it said the same thing. Wine prediction does not exist, creating a new experiment. Let it create. Probably it must have done it by now. There you go, wine prediction. Now it is logging the information to this. Let's wait. You should see run one here. Oh, there you go. Run one is just done 21 seconds ago. If I click on this run one, you will find all the parameters that are set default in this script. Let's go to this one, vim train.py. Let me do that. Vim train.py. Whatever data scientist configured here, for example, data scientist was logging information related to the test size. What is the test size? 0.9. Let's see if that information is logged. Let's go scroll down. Okay. Test rows is 9. Test size is 9. Train rows is 1. 10 minus 9 is 1. Yeah. Random state is 42. Test size is 0.9 because there are, this is the actual value. It got these values because there are only 10 lines in the CSV file. If we just do this, vim data wine sample.csv. So I'll set number. You will see that 10 lines, right? Ignore this first line. This is just the header. There are 10 lines here, out of which 0.9. So that's why it said 9 lines are used for testing and 1 line is used for training. Of course, it is bad, but I intentionally did that. Then these are the output performance of the model, the MSE, RMSE, R2. So this information is also pushed here. Why? Because even we log that information once the model is trained and once the model prediction is enabled, once the model is ready for prediction, we took these values as output, MSE, RMSE, R2, and we log that metrics. mlflow.log metric, mlflow.log metric, log metric. Log parameters is for the parameters used while training the algorithm, and log metrics is for metrics that we got once the model is ready to predict. The difference is simple. If you use log parameters, if data scientists use log params, the information will be stored inside this parameter box on the MLflow UI. Metrics. So if data scientist says mlflow.log metric, that information will be stored in the metrics. That's the only difference. Perfect. Now let's rerun this, but by changing the parameters, right? In the wine prediction, right now, there is only one prediction. I'll change this. Let me change something here. Vim train.py. I will change one of the parameters. Let me change, the test size from 0.9 to 0.2, which is actually ideal, 20% of the data. And let me keep the default run number as run2. To be honest, you can automate this. You don't have to change this every time. You can just use a counter. You can just use a simple script to update the run number. Anyways, Python 3 train.py. Okay, this time it will not create the experiment because wine prediction experiment is available. Directly, it will go ahead and create a new run within the experiment. Experiment is complete. Let's go back. So you can see the run2 here. Click on the run2. And now, if you look at the parameters. You will notice the parameters this time, test rows is 2, test size is 0.2. Let's see what is the performance or the metrics related to the model. You can clearly see the metrics are changed. This time MSE is 0.1, RMSE is 0.32, R2 is 0. Let's say if this is what data scientist is expecting, data scientist can go to run 2 and understand what parameters did they use. Perfect. So this is how data scientist makes use of MLflow. So all that data scientists have to do is start with set tracking URI. Of course, start with importing MLflow, then set tracking URI, then set experiment name. After that, data scientists have to log the parameters that they're using for the script, and also have to log the metrics once the model is ready for prediction. So these are the metrics, these are the parameters. That's all. Very simple changes. In the next lecture, I will show you how data scientists, MLOps engineers, management, how they can compare performance between two runs in an experiment, and also how they can use the most out of the MLflow platform. Box plot, which is easy way of understanding. Here you can see, okay, what is the run ID? This is just the ID, that's okay. What is the run name? Run 1, run 2. When is this executed? How much time did it take? What is the duration of execution? On top of that, they can also see the parameter comparison. So if you remember, in run 1 and run 2, we just modified test size. And if you look at all the parameters, only the test size is different. So test size changed from 0.9 to 0.2. That resulted in change of test rows as well as the train rows. Okay. Even the metric related comparison, that is for the performance of the model, can be seen here. What is the MSE? What is R2? What is efficiency? RMSE? These are some parameters that data scientists use. There are a lot of such parameters. We will learn more about them, but for now, just understand these are some metrics that data scientists track to understand which model is better or which version of the model is better. Not only this, of course, this gives a good amount of information, but data scientists can also go to a particular experiment. Like let's say they decided that run 2 is better. They can head to run 2. They can also see which git commit did they use. Because if they head to the git commit, they can actually see like this is the commit ID. And if they go to this particular commit in GitHub, they can also get the train.py file. Now imagine when data scientists are dealing with huge models and they have multiple data scientists in team, this information is very important. Not only the information of the data set, not only information about the metrics, but having an understanding of which version of the code did they use is also very important. So they can also get that from MLflow user interface. On top of that, if they are interested, they can also track the artifacts here. For example, within the same train.py that we used in the previous lecture, they can also say mlflow.log artifact. Artifact like the CSV file, the data set, right? Or artifact like the model, which is the output of the execution. They can also track artifacts within MLflow. Perfect. So this is how management, data scientists, or even MLOps engineers can use MLflow. It will be very useful when you have multiple experiments in the organization. Imagine wine prediction was run 1 year ago and they want to understand comparison between run 199 and run 200. It becomes very handy. MLflow platform becomes very, very handy. So this is about MLflow. I hope you got a very clear understanding. now that you all learned about MLflow, in the next 2 minutes, I will help you revise what you learned in this section. So it all starts with a problem statement. Data scientists within the organization, they work on different models, and for each model, they perform experiment. That is, they rerun the scripts multiple times by changing the parameters, by changing the algorithm to get the best and the efficient model. So it is important for them to track the execution of multiple runs so that they can go back and compare the runs. Previously, they do it on the Excel sheets, but it is a complete manual activity, and this is also not very trustable. So this is where MLOps comes into picture. So MLOps engineers introduce a platform called MLflow. Data scientists within their Python scripts, they can integrate MLflow so that experiment tracking is automated. And for this, there are two things organization has to do. So basically the MLOps engineers in the organization, they have to set up MLflow in a production manner, and data scientists within the organization, they have to instrument or log the information to the MLflow instance using Python MLflow module. Once this is done, whether it is management, MLOps engineers, data scientists, they can go back, use the user interface of MLflow and compare multiple runs. MLflow is also used for storing the artifacts. If they want to store artifact of a particular run, like they want to store the CSV file, they want to store the model that is created by each run, they can also do that in the MLflow platform. To make it very secure, MLOps engineers or the management can also introduce SSO to the MLflow platform. So this is about MLflow. What is model deployment and model serving? So model deployment and serving is a process of making trained machine learning model available to the end users. Let's try to understand using a very simple example. Imagine Netflix wants to build their recommendation model. We learned in section 1 about machine learning lifecycle. So when Netflix wants to build their model, data scientists within the organization, they will start with collecting the data, preparing the data set, cleaning the data set, feature engineering on top of it, selecting the algorithm, training the algorithm, finally evaluating the model. But if you observe carefully, all these activities are performed on the local environment of data scientist. So the output model is within the local environment of organization. Then ML engineers come into picture. They develop API for the model, integrate it into backend service. But even after that, model is within the organization environment. End of the day, what organization needs, of course, model can be very efficient, but this efficient model should be accessible to the end users. So Netflix wants their model to be in production. And this is where model deployment comes into picture. Now there are various stages that are involved in model deployment. For example, the first stage or the first step is to package the model. It can be in .pkl format or it can be as a container. Then store the model. Store multiple versions of the model within a model registry. And then deploy a specific version of the model onto the production environment or onto the lower environments first. But this is not the end of the process, because just deploying the model on a virtual environment or just deploying a model within the pod of Kubernetes cluster is not enough, because by just deploying, model cannot serve to the end users. During the deployment or as part of the deployment, MLOps engineers should also implement model serving. What does that mean? Providing the model with runtime environment, providing the model with resources. It can be CPU, it can be GPU. Also, making the API of the model available to the end users, that is exposing the API, setting up ingress, setting up load balancing, setting up auto scaling, setting up API gateway, if required, even services like CDN. So all the DevOps practices should also be implemented to the model that is in the production. Some of these activities like runtime is provided by model server. So model serving is part of model deployment, and it is a very critical activity as part of the model deployment. What I'm trying to say here, just deploying a model onto a virtual machine or pod within a Kubernetes cluster will not serve the purpose. During the deployment, the API of the model should be exposed to the end users. Model should be provided with good amount of resources. Model should be provided with runtime so that model can be inferenced or model can produce the output. You have to set up load balancing for the model, auto scaling for it, API gateway. Even if the model has to be globally accessed, then you should set up services like CDN. All of this comes under model serving, which is part of model deployment. Model deployment stage of your machine learning lifecycle. So this is about model deployment and model serving. Of course, there are various tools that can help you with model deployment and serving. We will try to understand those tools and also different model serving strategies in the future lectures of this section. In the previous lecture, we learned about model deployment and serving. In this lecture, let's understand popular ways in which MLOps engineers can implement model deployment and serving. We will learn about 4 popular strategies in this lecture. But before that, it is very important to understand model deployment only comes into picture once data scientist creates a model and ML engineers develop API for the model or creates a backend service for the model. Now, assuming this part is clear, let's go ahead and understand the strategies. The first one, and very simple one, is to deploy and serve the models using virtual machines. Now, in this strategy, MLOps engineers take the script files developed by the ML engineers. Usually, ML engineers develop API using Flask or Fast API. These are popular frameworks. Now, ML engineers take these script files, run the script files, and store the artifacts onto the virtual machine, on the local disk of the virtual machine. Now, for this artifact, which is basically API like /predict, MLOps engineers implement WSGI, they implement load balancing, they implement auto scaling, and put this entire infrastructure within virtual private cloud. So this way, the infrastructure is secure and model can be accessed by the end users using load balancer. So this is a very simple model deployment and serving strategy, which is good for small teams or when your organization deals with low to moderate traffic. Second strategy, deployment and serving through Kubernetes. Now, in this strategy, if you assume the same case where ML engineers used Flask or Fast API to develop the model. Now, in the second strategy, MLOps engineers initially build containers, package the backend service into container, and creates a pod through the deployment and deploys the pod onto the Kubernetes cluster. Then MLOps engineers implement the service, implement ingress, and other capabilities within the Kubernetes cluster. Now, this way, end users can access or model can be served using Kubernetes ingress. Now this is slightly complicated approach because you need understanding of Kubernetes. If you have good understanding of Kubernetes, this is more preferred approach than approach number 1. Third approach, managed MLOps or managed deployment and serving. So in these cases, MLOps engineers can go with cloud provider services like Amazon SageMaker. There are multiple services. I'm just taking example of a very popular managed MLOps service, that is Amazon SageMaker. Now in this case, MLOps engineers don't have to create any infrastructure. Using some drag and drops or using some clicks on the AWS console, MLOps engineers can implement model deployment and model service. But in this case, there is absolutely no control of the infrastructure. So you can go with this implementation if your organization is already in the Amazon ecosystem and if your organization has few MLOps engineers, or if your organization wants to offload lot of activities to the cloud provider. Now the fourth approach, which is getting very popular these days, is using Kserve. So Kserve again uses Kubernetes. Even model serving is performed using Kubernetes platform. But when it comes to Kserve, you don't need a lot of understanding of Kubernetes. Like you don't have to create the service, you don't have to create ingress, but Kserve offers some custom resource definitions. Using these custom resource definitions, you can offload lot of Kubernetes complexity. So if your organization is interested in deployment and serving through Kubernetes, but if your organization don't want to implement lot of Kubernetes related activities manually, they can go with Kserve. So Kserve is cloud native or Kubernetes native approach, but it implements some CRDs. MLOps engineers will use these CRDs, will provide YAML manifest to Kserve, and Kserve will implement a lot of things. For example, Kserve comes with a very good capability like Canary model of deployment. Using their CRDs, you can implement Canary model of deployment when you're dealing with latest version of the model. So these are 4 popular strategies which are implemented by MLOps engineers. One more time, the first strategy is using virtual machines. In this case, MLOps engineers take the script files developed by ML engineers. They run the script files, artifacts are generated. These artifacts are stored on the virtual machine. Then MLOps engineers implement WSGI gateways, they implement load balancer, autoscaler, and also put this entire infrastructure within virtual private cloud. So for the first approach, cloud knowledge is required. Second approach, the Kubernetes approach. We all know Kubernetes is a very popular platform. It is known for its scaling. You can even scale a Kubernetes cluster up to 10,000 Kubernetes nodes. So scaling is not a problem. If your organization is looking for expanding this model to large number of audience, they can go with the Kubernetes approach where MLOps engineers package the model into container, then it is deployed as a Kubernetes pod. Service is implemented, ingress is implemented, API gateway is implemented. All of these activities should be taken care by MLOps engineers. And in this approach, a very good Kubernetes knowledge is required. Third approach, managed MLOps approach, where MLOps engineers can go with cloud providers like Amazon and use their services like Amazon SageMaker. Fourth approach, which is getting very popular these days, is the Kserve approach. Kserve, Kubernetes native serving. Even in this case, MLOps engineers use Kubernetes, but lot of things are offloaded using Kserve provided custom resource definitions. MLOps engineers have to define the YAML manifest, and Kserve takes a lot of things that you have to do manually otherwise. In the future lectures, we will tackle each of these strategies. So we will first start with this strategy, then this, and finally learn about K-SER. So it's going to be very interesting and very important for MLOps in SNAS. So make sure you follow the next lectures as well as the sections. Okay, so to move to the next steps, there is a prerequisite. We need a sample model. And that's why I prepared this sample model, intent classifier model. So this GitHub repository has the script files to train this model and deploy the model onto the local environment. This is a very, very simple model. I'll quickly walk you through the source code, and then I'll also show you how to train and deploy the model onto the local environment. In the next lectures, we will use the same model to learn deployment strategies implemented by MLOps in SNAS. So to walk you through the source code, I will use Visual Studio Code so that it's much easier to understand. I clone the repository. So this repository has MD file, which first explains you what exactly is this project. So what does this say? This small project demonstrates training a tiny text classifier. So this model is a text classifier. Basically, imagine a chatbot, or imagine a chat service available on a website, and this chat service wants to understand the tone of the user's message. If user is greeting, or if user is asking a question, or if user is complaining about something. And this model predicts what exactly is the user's tone. So that's why it's called tiny text classifier. For example, if user says, "How are you?" or if user types, "How are you?" in the chat service, then this model tells the chat backend service, or this model predicts that user is greeting. Or let's say, if this model receives input, something like, "I want to cancel my subscription," then the model predicts that user's message is a question, or user's message is a complaint. So that is the purpose of this tiny model. Of course, I'll show you by running it as well. Saves the model artifact. So this GitHub repository is used to train the tiny text classifier, save the model artifact. That is, when you run one of the training files, it generates the artifact, and it also saves the artifact onto the local machine. Then it serves prediction using the Flask API on the /predict API. But Abhishek, where all of this is done? Very simple. So there is a folder called model. Within this folder, there is a file called train.py, and this train.py is taking the responsibility of training the model. So for example, it is training on this dataset. No external dataset is used because this is example and our focus is to learn deployment patterns. I kept the dataset very, very simple. So on this dataset, so this is the input data and this is the output. For example, if the model sees something like hi or hello, then it understands that, okay, user is basically greeting. And this particular input says how to reset password. Then model predicts this is a question. Cancel my subscription, complaint. Great service, praise. So this way, you can keep adding more elements to the input data, and you can also provide it with output so that you can enhance the performance of the model. Here, a very basic algorithm is used to train the algorithm on the training data. And finally, the output artifact is basically stored in the artifacts folder. So a folder called artifacts is created, and within that, model is saved in the .pkl format. That's it. And then you will see a message on the console saying that training process is complete. Now this is just a training process and model.pkl is created, but this entire thing is done by data scientists. What ML engineer does, ML engineers would implement this app.py. So basically ML engineers would write similar Flask or fast API scripts so that they expose the model using an API. So in this case, /predict is the API. When you run this app.py, so this app.py starts the model on the /predict API. Now users can pass their input, so they can just provide this model with the question or provide this model with the greeting, and from the /predict, response goes to the model. The same thing is explained in readme.md, right? And the next step here says how to run the model locally, training and running. The quick start process, first of all, install the Python virtual environment, then install all the dependencies. Again, the dependencies are very, very simple here. If you look at requirements.txt, there is just a Flask dependency, scikit-learn, because we are using the algorithm, joblab and pytest. In fact, pytest is not needed, but in future, if we add test cases, we need pytest. Okay, going back. This is for training the model. So model train.py, just run this command and it will create the artifact.pkl format in artifacts folder. Then this is the command to run the model on port 6000. If you want, you can run it on different port as well. And because this project does not have a user interface, again, my goal is to keep it very, very simple. So I did not create a HTML file or front-end service for it. We will use a curl request and pass users input here. For example, I want to cancel my subscription. And this request goes to the /predict API. From there, this request goes to intent model.pkl and this predicts if this is a question, if this is maybe a complaint or a greeting message. Now let's go ahead and run this on the local machine. We can run it from the terminal here, or we can also take a terminal from the machine. So let me pull my terminal just to make it very clear to you. Okay, so I'll switch to the directory where I have this code. In your case, you can clone the repository. Just use git clone and clone the repository. Of course, you will find every detail in the GitHub repository. Okay, cd downloads followed by the name of the folder where we have this source code, the intent classifier model. Okay, so we have all the files here. Now I'll start with setting up the virtual environment. I might already have one. Let me delete that. Okay. So here we are not implementing any deployment strategy in this lecture. We are only trying to get familiarized with the model because we will be using the same steps or we will be using the same model in the next lectures as well. Okay, so let's start with creating the virtual environment. Python 3-m venv.venv. Okay, let's source the virtual environment. Source.venv bin activate. Great. Now what would be the next thing we do? So we will install the dependencies. Python 3-m pip install -r requirements.txt. There you go. So all the dependencies are being installed. Once this is done, we will train the model. So how to train the model? Python 3 followed by model is the folder where we have train.py file. We will run train.py. Now this will take, maybe 20 to 30 seconds because here the algorithm is being trained on the data. And this is where it develops the function and it creates the model. So that's why in this step, you will see the execution takes time. Perfect. So it says train. That means now if I go to the model folder, we should see artifacts. And within the artifacts, we should see the intent model.pkl file. Awesome. So we have this intent model.pkl as well. So now we will run Python 3 app.py. So what is this app.py doing? It is just taking this intent model.pkl and it is exposing the model on the /predict API. That's it. Nothing beyond that. Okay. We learned in the very initial sections as well why this step is important, because you cannot expect the end user to download your model.pkl and run model.pkl. Companies like Netflix, companies like PayPal, they integrate these models into their backend applications. So their ML instance will create similar files, app.py or any relevant files, and they expose the models on the API, right? So that these models can be integrated into their systems. Great. So it says model is running on port 6000. Because we don't have user interface, we cannot access this on the browser, but we will take a duplicate tab. And on the duplicate tab, I will run this curl command. If you go to the README file, I already provided the curl command as well. So this is the curl, copy it, paste it here. So what is it doing? Curl, we are posting the information because we are posting the input to port 6000 /predict API, and it says, I want to cancel my subscription. Let's see what model predicts. So it says, this is a complaint. So you can see here, what does it say? This is a complaint. Let's try a different message, something like, okay, I'll again copy the curl command here, and this time I'll change the user input message to hi, what's up? Right? And this is, it's a greeting. Of course, I'm not trying to show you the efficiency of the model because the model is not very efficient. We used basic algorithm and we also used very less training data. With this training data, you cannot expect efficiency of the model. But the goal is to not complicate the process. That's why I'm using simple training data and I'm trying to explain you how things work in real time. Perfect. So this is how we inference the model, or this is how we pass input to the model and model returns us with the output. So till now, we only got familiarized with the code base. We learned what exactly is this project and we learned how to run this project locally. But this is not what MLOps engineers do. MLOps engineers take this to the production by implementing different deployment patterns that we will cover in the next sections. In this